The first in a new generation of low Earth orbit environmental satellites will deliver data more quickly and fast track weather satellite development. SwRI is designing and building the cutting edge QuickSounder satellite. How it will advance weather missions next on this episode of Technology Today. We live with technology, science, engineering, and the results of innovative research every day. Now, let's understand it better. You're listening to the Technology Today podcast, presented by Southwest Research Institute. From deep sea to deep space, we develop solutions to benefit humankind. Transcript and photos for this episode and all episodes are available at podcast.swri.org. Share the podcast and hit that subscribe button on your favorite podcast platform. Hello and welcome to Technology Today. I'm Lisa Pena. SwRI is collaborating with NASA and the National Oceanic and Atmospheric Administration, or NOAA, to design, build, and operate QuickSounder, the first in a new generation of low Earth orbit environmental satellites. The cost-effective QuickSounder will deliver temperature, moisture, and other weather data for NOAA's daily weather models, information we rely on to plan our day and to stay safe during severe weather. SwRI engineer and QuickSounder program manager Keith Smith and lead systems engineer for QuickSounder Steve Thompson join us now to tell us about this extraordinary satellite. Thank you for being here, Steve and Keith.
Thank you.
Yeah, thanks for having us.
All right, so tell us about this satellite, this technology. What is QuickSounder? What will it do?
Well, I can start by telling you this is QuickSounder is a NASA Class D mission. It's designed for a 3-year life with consumables for up to 5 years. And it's going to go into a sun-synchronous orbit at 824 kilometers of altitude. This is about a 400-kilogram spacecraft bus when bookkeeping launch vehicle margins. And it's got an 870-watt end-of-life solar array assembly at this time. Steve, I wanted to turn it over to you to talk about the approach that came out of the catalog bus and led us to our COTS component approach right now.
SwRI has 2 satellite models in the NASA Rapid Spacecraft Development Office catalog. That's known as Rapid 4. There's a number of vendors that have flight-proven spacecraft in the catalog. When the QuickSounder RFP came along, it was procured under or through the RSDO office at NASA Goddard. And we therefore started with the closest bus that we had to meet the requirements for QuickSounder. We started with the SWSP 100, which is our larger catalog bus, and adapted that to the specific requirements of the ATMS instrument for QuickSounder and the QuickSounder mission requirements.
Okay, so we're going to talk about what the ATMS instrument is. Keith, I did want to ask you, you used a term, you said sun synchronous. Can you explain what that means in relation to the satellite?
Yeah, it's essentially orbiting, it's facing the sun all the time.
It's a near twilight orbit, and sun synchronous is a special class of orbits where the nodal rotation matches the Earth's rotation around the sun. So we always have the same local time of day throughout the orbit at all times.
How does that benefit the satellite and the data it collects?
JPSS and other NOAA satellites in low Earth orbit fly in sun-synchronous orbits in order to continually monitor the same local times each day. So they, for JPSS and the earlier OPPOSE spacecraft, they collect data at 7:30 a.m. local time and at 1:30 p.m. local time in the afternoon. QuickSounder is going to bridge a gap by filling in data at near dawn dusk, 5:30 a.m. and 5:30 p.m., which will be a different data set than has been obtained previously.
All right, and all these data sets together inform these weather models that NOAA uses to give us our daily forecasts. Is that correct?
Yes, that's correct. NOAA runs their weather models 4 times per day, incorporating all the latest satellite data imagery from multiple spacecraft. That would include imagery that you would typically see on the Weather Channel from both the low Earth orbiting spacecraft and also from geosynchronous. Those are the GOES spacecraft.
Okay, so great. QuickSounder will be collecting data at 5:30 in the morning and 5:30 in the evening, adding to NOAA's weather models, which give us important weather information every day. So I wanted to go back to this explanation. We keep calling QuickSounder a low Earth orbit satellite. What is considered low Earth orbit, and how close to Earth is that?
So QuickSounder is flying at an altitude of 824 kilometers, which is about 535 miles in altitude.
Okay, so I mean, that's pretty close. You can drive that in a few hours. Is this about as low as they get?
I guess low Earth orbit is considered anywhere between 200 and 2,000 kilometers, which would be about 1,200 miles. And we have spacecraft at 340 to 370 kilometers. The International Space Station and Hubble. International Space Station is at about just over 400 kilometers. Hubble's at 540. There are Earth imagers out as far as 800 kilometers, so it's kind of a range. I will say for our first 2 spacecraft missions, our 8 microsat constellation Cygnus is operating, I believe, just under 540 kilometers right now. And Punch is planned for around 570 kilometers. So QuickSounder is going to be up above our first 2 constellations.
Okay, thank you. Great explanation of what that means. So NOAA has successfully operated these environmental satellites in low Earth orbit for more than 50 years now. So what do these types of satellites do?
The initial series of satellites called the Polar Operational Environmental Satellite System, which comprises over 10 missions, actually preceded what is now called JPSS. That's the Joint Polar Satellite System. Similar numbers in that series. These all carry instruments that monitor weather patterns and climate data, ocean temperatures, and a variety of other environmental variables. And they're used for forecasting and to monitor the environment, and specifically to look for changes over time, supporting research. That describes the past. I think you heard from Steve earlier. The past NOAA LEO missions have been crossing the equator 14 times a day, and they're giving full global coverage twice a day. And those are used by the National Weather Service for the forecasting that you see in your nightly news about 3 to 7 days in advance. Future NOAA LEO missions, the Near Earth Orbit Network is what's being planned after QuickSounder. They're going to produce higher resolution forecasts for weather prediction. They're looking for improvements by using LEO in timeliness and accuracy of forecasting for air quality hazards and enhanced chemistry sensors for the atmosphere. And they're also looking to help coastal communities through improved data collecting, I believe, optical data so they can see photoplankton and harmful algae blooms and things like that. So that's all future NOAA work in LEO.
All right. Really interesting and, of course, applicable to really our daily lives. We all depend on this weather information to plan our days. And in the future, we'll get even more information that will be helpful for all of us. So QuickSounder being added to this mix of these helpful satellites, and it's being called the first in a new generation of NOAA low Earth orbit environmental satellites. Will it improve data collection?
So QuickSounder as a Pathfinder mission is going to demonstrate that some of these operational observations can be obtained with a small commercial off-the-shelf based satellite bus on a compressed schedule. And to be more specific, by comparison to some of the past series satellites, we're hoping to demonstrate that we can build something at 1/10 the cost and 1/5 the schedule of previous spacecraft to collect these measurements.
How are you getting the cost down, and how are you developing this on a quicker time scale?
So we're leaning into components that have developed or been developed in the commercial sector of space over the last decade, often referred to as new space. These are components that are developed with constellation models in mind, where attrition is allowable and risk is acceptable, as long as it's understood and they try to quantify it. So what we're doing is we're working with NASA to go from extremely high reliability point designs to components that are developed with the idea of replacement in mind and high volume production in mind. And we're trying to harness all the cost and time savings that comes through using those components. And so that's what we're trying to assemble on QuickSounder. We're trying to demonstrate that we can fly this weather instrument using an assembly of spacecraft components developed by the commercial space marketplace.
The benefit to NASA and NOAA for a reduced schedule is the ability to infuse new technology much more frequently than they currently can. With their current development cycles of 10 years or even longer, once you include the instruments, which have to go through a separate design cycle that traditionally has been quite long. By the time a spacecraft like JPSS is launched, the technology is at least 10 years old, if not 15 years old or older. So that's why NOAA is trying to go in this new scenario where they can launch more frequently and more rapidly to get current technology up and benefit all of us in improving the weather forecast and doing that much more rapidly. So if we can cut the production cycles down from 10 years to 2 years, then much improved technology infusion for future missions.
Okay, yeah, that was going to be my next question. What benefit is there to that data collection process? But yeah, so because of the quicker timelines, you're going to get better technology up on that satellite. So that's pretty awesome. And again, tying it back into how it affects all of us in our daily lives. I mean, that's better information and data for us to plan our day around weather. So how big is the SwRI QuickSounder team?
Right now, it's about 15 full-time equivalents, but that labor is spread across 40 staff, across 40 subject matter experts. The disciplines involved change over the life cycle. So when you're in the design phase versus fabrication versus test, those are a different set of people. But I imagine we'll maintain that burn rate for some time. And that ultimately, we will touch more than half of our division. So we will probably touch about 80 staff or more by the time QuickSounder leaves the dock. That's in addition to at least 30 total staff presumed at a mix of subcontractors.
All right, so you have a pretty good sized team there. And Southwest Research Institute will design, build, and operate QuickSounder. Where is the team currently in this process?
The scope is broken into what happens in-house and what happens out-of-house. So I want to break down the scope and let you know there's direct efforts here at Southwest at the Institute, the overall programmatic and systems engineering and mission assurance. We're also building the spacecraft avionics. These would be the command and control electronics and those that move the data. And we're building the structure that bring together both the structural and the thermal design or implement them for QuickSounder. We have partner procurements. I mentioned flight software and guidance earlier, as well as propulsion. We're buying an S-band radio, a solar array, and a battery among the list of major components. And so there is parallel activity going on with those components. From an overall status perspective, we're about halfway between our system requirements review, which was in March, and our critical design review, which will be in November. And that is to say, we're wrapping up subsystem requirements, development and flow down, verification and planning. We have fabrication of flat-sat components in progress, both here at Southwest as well as at our vendors in our partner institutions. And then we have planning efforts that are started with respect to flight fabrication, observatory integration, and the Mission Operations Center out of the Boulder office. Our component timelines are they're in a similar place. Our components are somewhere past system requirements development. In fact, they're well past that because many of them, as I said, are commercial off the shelf. And they're gearing up for their engineering and flight builds as we speak.
Okay, so you kind of have these sub-teams working on different parts of the project. But if you could walk us through a typical day working on the satellite, I'd like to get a picture of what building a weather satellite for NASA and NOAA might look like.
I mentioned there were life cycle stages. You derive requirements, you design subsystems, you fabricate components, you functionally test them. And then you have to put the system together, put the spacecraft together, and run it through its environmental test paces. We have a steady stream of reviews interleaved at all levels of assembly. And so on any given day, there are different reviews associated with those stages of the life cycle that are ongoing at different levels of assembly. Could be as small as a component or a board, and could be as large as the entire spacecraft. Typical challenges across that array, they include design gaps at commercial interfaces, perhaps signal types that are expected, ranges that are expected electrically, or even load limits that we need to provide ride quality for on the spacecraft. You can have fabrication issues during the build. To give you an example there, we've had boards come in, bare boards that have we've had them populated with, something on the order of $300,000 worth of flight components, only to discover that the solder had bubbles because the board vendor that we bought the board from had some process problems. And so we've had to scrap a pretty significant flight board. That's an example of a fabrication issue, and there are others. You can run into corner cases not caught during lower levels of testing. So a radio that may perform well at its box level test may not play so well with a ground station modem once the two are plugged into each other, even though both of them presumably meet the same standard. They have different interpretations, and the standards are silent sometimes on some of the nuances of signal flows. And so those kinds of corner cases, or corner cases resulting from environmental exercise, operating at temperature, or things like that, those may not be caught during lower level testing, and they have to be debugged at a higher level of assembly, which abstracts it abstracts the symptoms from what the root cause is, and it takes quite a bit to unpack.
Yeah, I would add just a couple things there. So one of our ongoing challenges is that we don't know yet what launch vehicle we're flying on, and that since we're already in the process of building flight hardware, that's a real challenge. We have to envelope the environments to make sure that we're able to fly on any of the candidates that are selected. So that introduces some unknowns into our design process. Other problems that we have run into recently are supplier issues, that suppliers that we thought were going to be able to provide the hardware that we needed when we needed it have not been able to do so for a variety of reasons. And we need to go out and quickly find other vendors to provide that same functionality without disrupting our design too much, since we've already got boards in fabrication. So that's been a challenge. But on a daily basis, as Keith said, we're really just kind of working through all of those interfaces, working through the design issues as we get ready for our intermediate reviews, which we're calling engineering peer reviews in advance of CDR. And ultimately, we'll be ready to move into flight fabrication actually before the CDR this fall. We are taking some risk in our schedule by doing things concurrently, and accepting that risk that something that we build or procure may turn out ultimately to be wrong in some way, and we'll have to go back and correct that. But we're trying to keep that to a minimum. That's our challenge.
Yes, it sounds like the team is juggling a lot of little issues, and there with any project there are challenges that come up. It sounds like you are overcoming those quickly and pretty much staying on track.
That's right. We're heading towards a February 2026 launch, which is we're shipping to the launch site almost exactly 2 years after contract award, and we're on schedule.
Yeah, so we want to stress 2 years after the contract award, when the development of these types of satellites usually takes up to 10 years. So really quick timeline here. Low Earth orbit satellites provide the bulk of numerical weather prediction model data, as you mentioned, used for those 3 to 7 day forecasts. And we all look at these forecasts every day to plan our days and maybe what we're going to wear, and if we need to grab an umbrella. So how will QuickSounder improve weather forecasts? Will it improve weather forecasts?
It does improve our weather forecasting ability in a limited way, in that we're able to fill in gaps that we currently have in the data collection. QuickSounder will be collecting data specifically at those local times of 5:30 a.m. and 5:30 p.m., which will fold into the models. And the interesting thing about the ATMS instrument, which is the Advanced Technology Microwave Sounder, is that it's a 22-channel sounder that operates between 24 and 180 gigahertz, very high-frequency microwave, which allows it to see through clouds and, in essence, provide X-ray images, if you will, of storms and clouds, hurricanes, to determine the temperature and water content, which all goes into the weather models. So while QuickSounder itself is going to contribute in some small way to improve weather forecasting, it's really its role as a pathfinder that's going to open up a new way of doing business for NOAA, where they can put up constellations of satellites, 30, 40, that measure weather data much more frequently, but with only 1 or 2 instruments per spacecraft instead of 6 or 8 that are currently on JPSS.
All right, so more satellites means more data and more information for the public. So we're in hurricane season now. Already had a couple named storms. Will QuickSounder be useful during hurricane season? We really rely on that type of data during hurricane season to save lives and property. Will QuickSounder contribute to that important hurricane data?
It does contribute. It provides the weather, the specific parameters that it's measuring are water content and temperature.
Okay, so kind of going back to what we talked about before, when QuickSounder's up there, it will collect data that will be useful in any kind of weather, hurricanes included.
That's right.
Okay, so we have mentioned the ATMS instrument a couple of times. So let's talk about this instrument. What is it? What does it do?
So it's the Advanced Technology Microwave Sounder, and the name is a little bit of a misnomer, because this particular instrument that we're going to fly was built in 2004 for part of the JPSS program. It was built as an engineering model and has been a hangar queen for 20 years. But recently, Northrop Grumman was awarded a contract by NOAA to refurbish it for flight. And that's what we're going to put onto QuickSounder as a proof of concept, but also to fill in the gaps, as I mentioned, in local time. But what is important about the instrument itself is its ability to collect the weather temperature, the weather data, temperature, and water vapor at a range of altitudes, regardless of cloud cover. So it measures from, I believe, 10 kilometers up to about 50-kilometer altitude, so all through the stratosphere to measure those parameters.
Okay, and just to clarify, the ATMS instrument, are there others that are already on other satellites and this particular unit has been sitting in the warehouse, or is this the one and only ATMS instrument?
Yeah, they are currently on orbit. The ATMS works alongside something called a cross-track infrared sounder. As Steve mentioned, QuickSounder can use microwaves to see through the clouds. Not true for the infrared sounder. And this pair of instruments is currently on at least four spacecraft, including NPP, NOAA 20, and NOAA 21. And it will fly on the JPSS 3 and 4 satellites once they're launched.
As we said, QuickSounder is serving as a prototype for this next generation of weather satellites. So what's next for this technology once the prototype is successful? What do you envision for the future of QuickSounder?
QuickSounder is really, it's a skunkworks project at NASA Goddard. They have an extremely small team. I believe they have 7 regular members, a couple of other supporting cast. But at our weekly telecons, typically there's only 4 on the phone. This is quite different than some of our other missions with NASA Goddard, where there's a team sometimes greater than 20 supporting the mission. They have a very light touch in their oversight, and they're working very, very hard with us to change requirements that impact cost and schedule to achieve the goal of this tech demo. We're embracing a quantified risk approach. An example of that is we're accepting commercial off-the-shelf products with a top-down review. How did that component do on its previous mission? In some cases, regardless of orbit or only with minor deference to the orbit type, rather than the traditional bottoms-up analytical review of every electronic component inside the boxes that are then assembled to become the spacecraft. My hope here is that this project will help us all find better, faster, cheaper through the innovations that are coming out of the commercial part of the space industry right now.
To add to that, as to the future of NEON for NOAA and what they're going to do, they're looking to fly a constellation that each of the spacecraft would have different instruments. So there would be maybe 6 or 8 that are flying something like ATMS, but newer technology. There will be others that are flying a version of the CRIS, which is the infrared imager, and various other sensors. But because they're going to be proliferated and flying multiple copies of each, they'll be able to get more frequent data, much more global coverage than they currently get, which will improve the fidelity of the weather modeling and improve the fidelity of the forecast. And then they will also be able to introduce the new technology that we touched on earlier, where they can fly new sensors that haven't been flight proven yet. They can take a chance on a $50 million spacecraft that flies a sensor that may or may not work. And if they can do it in 2 or 3 years, get the answer, find out that it works, put up 6 or 8 of those in another 3 years, that's still much less than the 10-year cycle that it took to design and build and launch a single JPSS spacecraft.
All right. So more flexibility, testing this advanced technology. And, if it works, getting us better, faster forecast models. So really interesting. QuickSounder has a lot of promise there. Okay, so on episode 10 of the podcast back in August 2019, we learned about NASA's Cyclone Global Navigation Satellite System, or CYGNSS. So Keith, you were the mechanical lead for that mission. Is QuickSounder building upon the development of CYGNSS? Are some lessons learned on that project being applied to this project?
Yeah, we do try to capture lessons learned on all of our projects, again, at different levels of assembly. and then we try to apply them forward. It's always a body of work that can be improved. But for Cygnus, what struck me is that we designed that spacecraft very much at the component level. For example, we selected our own sun sensors. The mission that came after that was Punch, and because of some of the lessons learned on Cygnus, we did not select our own sun sensors, but rather we abstracted ourselves and we bought subsystems at a higher level of assembly. So we let our attitude, determination, and control lead select all of the sensors for the spacecraft, and we bought them all from the same company. We learned lessons there as well, problems that were created in that mode of operation, that business model. And I would say at this time, QuickSounder is taking a hybrid approach, and in that we're driving the design control to a level that's tailored by each subsystem lead. So we have a variation, we have a mixed bag. We have a propulsion lead that's building our propulsion units all at one shop. And so that's a package deal. But in another area, we've combined subsystem leads, like flight software and ADCS as an example. It would be the attitude determination. Those two subsystems are combined from a subject matter expertise perspective. And we're working with an external organization that has a lot of commercial off-the-shelf on-orbit experience right now with both of those subsystems. And we're having them help direct component procurements to build our flight software and attitude determination system for QuickSounder.
And I think this is a great time to point out that the Institute does this in so many areas. We build off of these prior projects, and that's why we're considered experts, and we have all this experience in these various fields, like your team, learning from Cygnus, going to Punch, and then building off that and knowing what might work best for QuickSounder. So that's great. I love to see the continuity, the bringing that experience to the table for your current project. One of the things we like to do on the podcast is to get to know the scientists and engineers behind the work. What was your career path?
I started my career as a material science intern, building composite materials for structural, thermal, and electrical insulation. I spent some time in the ground vehicle industry, doing empirical data acquisition and life testing, accelerated life testing, and then a couple of years in high volume production. Some of these experiences led me to Southwest Research about 21, I think coming up on 22 years ago, where I had the opportunity to learn more about the front end design work, stress analysis of aircraft and submersibles. And I came to the space sector in 2006 as a systems engineer for spacecraft avionics. My time was spent troubleshooting electrical problems at board interfaces and pushing boxes through environmental tests. Our Cygnus spacecraft constellation came along, and I had the opportunity to be the mechanical systems lead, followed by Punch as the spacecraft lead. And I will say that QuickSounder was very much an unplanned surprise for me personally, but a welcome opportunity. I really do enjoy working across large teams of discipline experts who all have developed themselves in ways that there's not enough time on Earth for me to develop myself in all those different directions. And projects like Cygnus, Punch, and QuickSounder offer that opportunity, as opposed to the industries I was in prior, wherein I had a much smaller set of blinders, a much more focused problem to solve before I moved on. So that's my enjoyment of spacecraft.
Steve, tell us a little bit about your journey. How did you get to this project where you are today?
Yeah. So my career started as a mission analyst and mission simulation for large national systems at the time. And then I transitioned into working on small spacecraft for the Department of Defense, the Air Force at the time. It was the Space Test Program. And we built a number of small spacecraft before small spacecraft were a thing. The purpose of those were to fly new technology for the DoD, Air Force, and other agencies. So that's how I got introduced into both spacecraft design and also small spacecraft. From there, I worked on a number of different companies over the years. Spectrum Astro was one, Orbital Sciences, and most recently, I was at Millennium Space Systems, all of which specialized in small spacecraft. And I came to SwRI about a year and a half ago, with my primary role being spacecraft system engineering and new business. I worked on the QuickSounder proposal among several other proposals, and we won, and here we are.
Okay, I love asking about, I think it's important to ask about career paths because you never know who's listening, a young person out there who thinks this sounds like a cool thing to do in the future. And I always like to know, how did you get here? So really important work you're doing and interesting work. So I really enjoyed hearing your backstories. Thank you both for sharing. So at the Institute, our mission is to conduct research and development to benefit humankind. And one of my favorite questions to ask on the podcast is, how does this project benefit humankind?
It's really a pathfinder or proof of concept for a new way that NOAA is going to do a better job of procuring spacecraft, building spacecraft, designing spacecraft in the future so that we all have better weather forecasts. Maybe we'll have someday 10, 14-day weather forecasts that are just as accurate as what we have now 3 days out.
Yes, exactly. Keith, fast, accurate weather information keeps us all prepared and safe. So QuickSounder is really leading the way for this satellite development and getting us better data. So I really want to thank you both, Keith and Steve. Thank you for being here and telling us about this important research and development you are leading.
Well, thank you. It was fun.
Yeah, thank you.
And thank you to our listeners for learning along with us today. You can hear all Technology Today episodes and see photos and complete transcripts at podcast.swri.org. Remember to share our podcast and subscribe on your favorite podcast platform. Want to see what else we're up to? Connect with Southwest Research Institute on Facebook, Instagram, X, LinkedIn, and YouTube. Check out the Technology Today magazine at technologytoday.swri.org. And now is a great time to become an SwRI problem solver. Visit our career page at swri.jobs. Ian McKinney and Brian Ortiz are the podcast audio engineers and editors. I am producer and host Lisa Pena. Thanks for listening.